Okay, we're live, guys, and I've got the record button on. Thank you. Today, we wanted to get, I wanted to get you introduced to using Arduinos to control LEDs. Of course, what I'm going to teach you here transfers directly over to how to control a servo or a DC motor, a lot of other little things. So before I do anything else, I want to kind of give you a commercial, okay? Instead of changing cameras, and let me see if I can hold this up. Can everybody see that? Yeah, this is a little starter kit that I got, okay? Cost me 20 bucks. So it's been well worth it. It allows you to do a lot of little breadboarding without having to worry about soldering and wasting a lot of time doing that. You can quickly move wires around, test things out. It's very much worth the 20 bucks, okay? So if you're getting started, I would suggest doing that. It even comes with an Uno, Arduino Uno in it. So you get the brain to come with it, okay? Everything you need to do these little exercises today comes out of that kit. So just keep that in mind. So with that said, I'm gonna go over here and share the screen and get things started. The first thing I want to do is kind of introduce you to some, got the wrong button there, guys. Introduce you to some of the things we'll be using today. I don't know, I'm talking with an audience that I don't know all your backgrounds, and I'm assuming I'm talking to a broad audience. Some of you have knowledge about what I'm talking about. Some of you are seeing this for the first time. So I'm kind of having to mix my presentation to cover those bases. These are called breadboards, and they're important in that they become your electrical circuit, the basis for your electrical circuit. And they're designed to work with IC chips, transistors, and resistors and other electrical components. So to just cover the bases here, if you can look, can you see my mouse? Can everybody? Yep. Okay, so you can see me pointing at the minus and the plus here. These are power strips. So this minus runs all the way down the board where that blue line is. And this plus runs all the way down the board where the red line is. So that allows you to pick up power up and down that board wherever it's convenient for you, okay? Now, the board above is a slightly different design. You can see that instead of having two along the edge, it only has one. This serves the same thing. This is a power bus, and this is a power bus. But the idea here being is that you put negative on one side and positive on the other side, okay? Where this board offers you the convenience of being able to do it from either side. Other than that, they're the same. The next thing to note is that this gap down the middle, okay? That gap down the middle separates your power into two zones. This row of 5 and this row of 5 are independent of each other. However, this row of 5 is one electrical connection. So you can plug into any one of those 5 points, it's the same electrical point. And the same is true on this side. This row of 5 is the same electrical point. So you can see that up and down the board here. We've got rows of 5 constantly up and down, giving you plenty of room to be able to plug your little wires into, okay? So with that said, let me see if I can, oh, I gotta hide you guys here for a second so I can move to the next slide. There we go. I'm just bringing up the edge of the board so you can see it a little bit more clarity. You can see this board cost me a little bit more. It numbers the rows and the columns for me. So that, and this one is just blank. It's a little cheaper. Okay,
Hey, Jim, can I ask a question?
sure.
Is there what gauge of wire? Is there a fixed gauge, set gauge?
I've had all the way up to 22 gauge in here. 22 gauges, almost to the point where you're going to damage it. Okay, so I would say 20 gauge and below.
Okay, thanks.
The kit comes with the little wires included. Okay, you'll see me using them. Here I just wanted to demonstrate and show you how I laid an IC chip across that gap in the board. That means this row of pins is now lined up with these rows of plugins, okay? This gap isolates the opposite side, so this row of pins is now lined up with this row of plugins. So I have 4 left on each side where I can plug into each pin on that IC chip. So that kind of gives you a background on how to use a breadboard and why they're so powerful. Okay, you can quickly move a wire from here, one lead to the other, and without having to unsolder and worry about damaging parts or anything. This, my friends, is the Arduino Uno Pin Out. So we'll spend just a minute going over what the Uno does for you and how versatile it is. I'm going to blow it up here a little bit more. Okay, down at the bottom, it gives you a legend like a map, so you can follow along with the colors and everything and see what's going on, how they're being used. For example, down here, the digital pins are in the orange. That's this row of orange right through here, the dark orange. So you can see D2, D3, D4, D5. So digital pins are strictly on and off. Okay, either there's a voltage there or there is no voltage there. But the pins often are used for more than one purpose. And you'll see us do that today. We'll use digital pins, and then you'll come over here on the opposite side. You see here we have digitals 14 through 19, but they're also labeled A0 through A5. That means we have 5 analog input pins. Okay, so not only can we see digital inputs, but we can see analog inputs. And if you're not familiar with the difference between digital and analog, I have a little graph coming up here shortly that will demonstrate that. So we're going to focus on using the digital pins and the analog pins. But there are also transmit and receive pins, TX and RX, right here, digital 1, digital 0. So if you want to talk to this device, you can talk to it on these 2 pins. However, if you're using them for transmit, then of course you can't use them as digital inputs and digital outputs. So it's an or situation. You have to pick what purpose you're going to use that pin for. And I'll demonstrate how you tell the processor how you're going to use that. There's 3 LEDs, or I should say 4 LEDs on this board. One down here is simply on anytime there's power. So you know you got 5 volts to the board. Okay. Then you have the transmit and receive LEDs. And if you're talking to this board, you'll see those little lights twinkle back and forth because when it sees the transmit, that means it's being queried. I'm asking you something. And when you see the RX blink, that means I'm answering what you asked me. So they query back and forth as the computer talks to this board, or the board talks to a monitor, which you'll see me use, okay? And then over here, this is the built-in pin, LED, that you use for testing. And our first little program is going to be using this. It's called Blink. All these cards come with a program on them. So as soon as you plug 5 volts to this board, you're going to see this little LED start to blink. because from the factory, it comes loaded with this little test program. And that tells you, hey, everything's working, okay? I got power to the board and the braid sees it and it's running a program. So the card's basically working. So that's the first program we'll run. We'll show you how it gets loaded, and we'll do that. Then we'll advance on to some of the questions you guys had about how do you dim an LED and do different things with them. So let me now drop this back down. We'll move on to the next chip. This is the Arduino Nano. It does exactly the same thing that the Uno does, but it's much smaller. So I'm going to switch my camera here for a second, and I'm going to show you the difference between them. Get down here where I can, oh, I have to get out of this share. Sorry, guys. Isn't this interesting? Tested all this last night and worked like a champ. Today it won't switch cameras for me.
Hey, Jim, we did
You
see
had
it.
it for a second.
Oh, did I?
Yeah, it was
You're
working.
on the board, Jim. You can see the board in the Arduino.
Yeah.
Oh, okay. Thank you, guys. You can see the board now.
Yeah.
We see
All
your
right.
board and your hand moving.
Okay. Now, I'm laying the Arduino next to it. Can you see the physical difference in size there? See how much smaller that Nano is compared to that Uno?
Yes.
Okay. So if you want to use this inside one of maybe your HO structures or something, maybe you want to use the Nano instead of the Uno, because it'll fit in a much smaller space, but it does exactly the same thing. Okay, so I just wanted to point that out. Let me go back to my screen share now. Again, all the pins are labeled on here the same way as on the Uno, and some of them have a double purpose, just like down here again. D1, D0 can also be your receive and transmit lines. I want to point out also that there's a couple of ways to power these boards. One way is just to plug into your USB port up here and power it from your computer. And that's what I'll be doing today. A second way to do that is down here, this 5 volts. You plug it in right on this pin, 5 volts in ground, and you power it from that connection. So it can come off of a power supply if you want it to. There's an interesting thing about these. They bring 5 volts in, but they also allow you to have 3.3 volts out. And why that's of interest is that a lot of your modern day electronics is designed to work on 3.3 volts, low power, okay? And so a lot of the sensors that you hook up to these devices are 3.3 volts. So the Nano and the Uno allow you to feed out the 3.3 volts to your sensor device and power it directly. That saves you from having to have another power supply and everything. So that's a convenient thing, again, for learning and testing and developing on. All right, one more slide here before we get into the meat of what we're doing today. Just wanted to show you a little bit about the LED itself. We've all seen the LEDs. How many of you are familiar with the short lead, long lead, and what it means? Okay, I see a couple heads shaking there. The short lead is the negative side, or the cathode, and the long lead is the anode side. or the positive side. Another way you can tell on a lot of LEDs is one side will have a flat surface to it. That's the negative side. Cheaper ones don't have that. They'll be perfectly round. So just to let you know, and then on this side is the schematic symbol for what you can see an LED. Okay, see the two little arrows pointing out? That tells you this is a light emitting diode instead of a regular diode. And the cathode and the anode, a negative and positive side. Little freebie here, guys. Until the vacuum tube was discovered, nobody knew which direction electrons flowed. So it was just decided by convention that electrons flowed from the positive side of a battery to the negative side of the battery. That's why the arrow points in the direction it's pointed. That's called conventional current flow. But when the cathode and the anode, when the vacuum tube came along and we had a cathode and an anode, it was discovered that the electrons actually moved from the negative side to the positive side, but the arrows were never reversed. So in modern day electronics, when you see these arrows, they're pointed the wrong direction, but for a reason, okay? And that's called conventional current flow. And physicists use it to remember the direction of what they call hole flow. Because every time an electron moves from one atom to another, it leaves a hole. So they call it hole flow. And that's how they study it and develop it. So I'm going to set this aside and we'll look at this little sheet here. This is just a sheet to tell you, you know more than you think you know about programming. And my goal today is not to make you a programmer, but if you don't understand what you're looking at, then it doesn't make much sense to watch these little light bulbs blink back and forth. So I just want you to know you actually know more about programming than you realize. And so to prove that point, I'm going to show you how a recipe in a recipe book compares to what Arduino calls a sketch. Other computer programs just call it a program, okay? Arduino calls it a sketch. So in a recipe, when you flip open that book, the first thing you usually see is the chef's comments about the recipe and the credits, right? They may be as simple as, this recipe comes from my grandma, okay? But they're credits. So, and then also, you may see them say, I want you to refer also to page 97 about how to make a perfect pie crust, right? So we can assume this recipe is about how to make a pie now, right? So instead of writing everything in here about how to write a pie, make a pie crust, it just refers you to another section, another page where it's all explained, and all you do is run over there and look at it and come back, okay? Now, on our sketch, the programmers do the same thing. They usually open up the program with their comments, where they give tell you what kind of a license it's been released under. They may tell you this is based on John Doe's program, and I've expanded on it to make it, you know, fit my need, and give you credits like that. And then you'll see a little term called include. Okay, this tells the compiler to run out and get this piece of code and pull it in and use it. So it's much like going over here and saying, go see this page, okay, for how to make a pie crust. Here, the programmer is saying, I want you to include a program called wire.h and use that code, and then we don't have to write it. We just get to borrow it and use it, okay? So that's what an include does for you. Going back to our recipe, you see that the next thing you usually see in the book is the list of ingredients, okay? You're gonna need 2 cans of apples, you're gonna need some cinnamon, whatever the ingredients are. You'll see them listed there. And perhaps a couple of preparation steps, you know, like it's best if you chill the pan first, or things of that nature. So coming over to our sketch, before we do any programming, the first thing we do is declare variables and constants. These are our ingredients. What are we going to use in our program? Okay, and just leave it at that right now. We're not going to go any deeper. You'll see it when we get into the program. And then there's a thing called setup. And setup is things that you do one time and only one time when you start the program. And you can compare those to maybe the preparation steps over here in your recipe. So setup begins with this little curly brace and ends with a curly brace, and you'll see that in our code. Okay, back to our recipe, then you see the instructions, and you'll see terms in the instructions like mix, blend, stir, pour, bake, telling you how to use the above ingredients, how to mix them to successfully make a pie. In our sketch, we have what we call the loop. Again, it starts with a curly brace and ends with a curly brace, and all the instructions between those braces gets repeated over and over again. That's where the term loop comes in. Nice English word that illustrates what we're doing. We're going to run through this code once. When we get to the bottom, we're going to come back to the top, do it again. When we get to the bottom, we'll come back to the top and do it again. Okay, we're going to continuously loop through that code. So I hope that illustrates you knew more than you thought you knew about programming. So let me drop that down out of our way. And let's take a look. Let's do a little programming. Okay, do I have Arduino? Yeah, I have it open. If I double click that, it'll open, right? And it always opens, if you programmed before, it'll always open with the last program you did. So in our case, I have it opened up to Blink. This text in here is gray. Can everybody kind of see that? You don't have to focus too much on reading it, but all this is the comments and the licensing, okay, that I told you that the programmers do. Okay, here he's saying it's modified on this date by Scott Fitzgerald, modified on this date by Arturo, right, and modified on this date by Colby. So this piece of code's gone through a couple of revisions, okay, and it's been licensed into the public domain right here. Okay, so that's just all that introductory, got it from my grandma type information. Okay, and a reference where you can go to get all this stuff. The next thing we see is a comment. You can tell comments in these programs, any line that starts with a double slash. Let me let Kelly in here. Okay, any line that starts with a double slash is just for the programmer. That's some kind of a comment that the programmer wants to share with you. Okay, so he's telling you, all right, I'm setting this program up once. When you press and reset the power on the board, it'll rerun it again. So here we have the little setup program that I was telling you about that gets run once. So see the curly Q right there, brace? The IDE, Integrated Development Environment, works with you and helps you. So if I click my cursor next to this curly brace, it shows me the matching ending brace down here. See how it's highlighted? So that's the beginning and the end of that function, the setup function. And there's only one thing we do in there. We tell it how we're going to use the pins. So we got pin up mode, LED built in as an output. So let's stop right there. I want to pull up a little piece of code here. Okay, this is from the Arduino website, and it's the program Blink. And this is what we're getting ready to talk about. So you can come here to Arduino and you can get all this help online how to do this little program. So I'm kind of using these like handouts. So when you get this, I'll have it recorded and of course put up on the website. You can come up here and see these addresses, right? And you can copy them and go to these sites. So that's my electronic handout, guys, okay? So the first thing we're gonna do is we're gonna drop down here and it's gonna tell you quickly that this has a built-in LED, okay, on pin 13. But it's gonna tell you that not all boards, not all the Arduino boards put that LED on the same pin. Most of them do, but there's a couple of exceptions. So this is the list of the type of Arduino boards you can get and what pin that built-in LED is on. And we're using the Uno. So digital pin 13 is the pin we're interested in for the built-in LED. So we'll come on down here and here's an illustration of what we're going to do. Okay, here's the Arduino Uno. Here's pin 13 and here's ground. So we're going to take the LED, okay, we're going to take the negative side, put it to ground. The positive side, we'll link it in with a resistor and tie it to pin 13. Now, why the resistor? We use the resistor because 5 volts is too much for the LED. LED is designed to work with 3 volts. So we have to get rid of that power somehow. So just real quickly, as a reference for you guys, if I can get past my little my pop-up wants to drop down in my way, okay. Real quickly. For those of you that aren't real familiar with Ohm's law and how to use it, again, watch this address up here and you can come back to this page. Here you see our basic circuit, right? We got a power source, we got the LED, and we got the resistor. So we want to know what size resistor to use there. What we do is we come over here and use their calculator, voltage source. How are we powering this LED? Well, we're powering it from the 5 volt output pin. So we tell it we're going to source it with 5 volts. Then it asks, how much voltage does the LED use? Well, they all vary slightly, but if you don't have the data sheet and the spec sheet, it's safe to assume it's going to use 3 volts. Then it says, okay, how much current does the LED use? Again, the spec sheet will tell you. Now, why is that important? Different color of LEDs use different current levels to achieve brightness. If you put the same current into a yellow LED that you put into a red LED, the yellow LED is going to look like it's only half turned on. It just won't have the same brightness, okay? So you have to put more current into those. That's why it asks what current you're using, okay? But if you don't know, it's always safe to say it's going to use 20 milliamps. And again, over here, make sure this is set to milliamps. You got to drop down amp or milliamp, okay? And in your spec sheet, you can look and find that, looking for the term VLED, ILED. Now, once you've given the calculator those values, it will calculate the resistance and the power. So you just hit calculate, and it tells you you need to use a 100 ohm resistor, okay, and that's going to produce 0.06 watts of power. Now that's not a whole lot of power, okay? And if you touch that resistor, you'll never know that it's heating up. But that's the purpose of that resistor. The resistor is to consume that extra 2 volts of power. And it does that by generating heat. So that's why we have to size the wattage for these things. But with an LED, it's always safe to say I can use an 1/8 watt resistor, or the most common size resistor is a 1/4 watt. Okay, so this is where you can go to find out what size resistor you want to use, and you don't have to be a master of it. Just remember, by default, you can use 20 mils and 3 volts, and you'll be in the ballpark and safe. And if it's not bright enough, change the value of the resistor a little bit. So let's go back to what we were looking at. We saw now how it's hooked up, and pin 13, again, is the same as this built-in LED, okay, that we're talking about in our little test code. So we'll go back to the test code. We set it up. All we're doing with pin mode is we're telling the Arduino that we're going to use the LED underscore built-in, which is a constant that's defined for us just in the programming language. Okay, we're telling it to use that pin, which it represents pin 13, as an output instead of an input. So we've done all the setup. Yeah.
Can I ask a question again?
Go
Can
ahead,
you go
Jeff.
back? Can you go back to that previous slide where you've got it hooked up to the Arduino,
Okay.
the LED?
This one.
So, yeah. Oh, okay. Maybe it's just the way it looks there, but it looks like the ground is hooked up to the anode. Am I just seeing that wrong?
Yeah, you're right. The kink in the wire usually indicates the negative side. Okay, so the illustration could have it backwards, but
Okay.
but that's not a guarantee. Okay.
Actually,
So-
if you look at it, the flat side of the LED, which is on the left side of the, that's the cathode, and it's going to the ground. So I think it's right.
You're right. I see the ridge cap along here, guys, and it ends on this end. So that's the flat end of that LED. That's what's being pointed out. Okay. So it looks like it's hooked up correctly.
Okay, thank you.
You're welcome. All right, so we've set up the pin that we want to use. Then we're going to drop down here. Here's our loop circuit. See here again, I got the curly brace and the ending curly brace. So everything between these two braces just constantly gets repeated and repeated. The next instruction that we're going to use, the next programming statement, I should say, that we're going to use is the digital write. Now, I want to take just a second here and make you see again that you kind of understand this term more than you think. Let's take your brain. I mean, your brain is now the processor. If you want to get something out of your brain and onto a piece of paper, you have to pick up a pencil or a pen and you have to write it onto that piece of paper. So when we use the term write, that means we want to send something out. Later, you'll see me using the term digital read. So if you want to get something into your brain, you have to pick up the piece of paper and put it in front of your eyes. You have to read it to get it into the brain, okay? So digital read, digital write are that simple. It's either send something out or pull something in, okay? In this case, we want to send something out to pin 13, the built-in LED. Again, we're going to use a built-in word that the computer knows called high. It means turn it on. Put 5 volts there, okay? look at these, another little programming tip here that the IDE helps you with. See how our text are in different colors? Okay, this is a built-in function in orange. These magenta, not magenta, what, blue? Don't know what color to call those. Light blue, those are defined words that the computer already knows. So it puts them in a different color and says, hey, I know what these are. You can use those, okay? So once we
Jim?
write 5 volts out to that pin, the next thing we're gonna do is we're gonna drop down and delay. Now delay means exactly what you expect it to mean. Oh, hold it back up. Let's take a little time here, okay? And it's gonna stop this program. And I mean literally, that processor is gonna do nothing but sit there. And this is one of those baby, easy to use programming functions that's not recommended because the processor literally stops and does nothing while you're using it. There's other ways to do this, but this is a simple beginner's way to do this. Okay, so we're going to delay, but how long are we going to delay? So we tell it we want to delay for 1,000. Delay measures things in milliseconds. So we're going to delay for 1,000 milliseconds or 1 second. And that's a time for our eyeball to catch up. Because if we didn't put that delay in there, things would happen so fast that we might not see it on at all, or we may never see it go off. So we delay it for the eyeball to be able to see it. Then the next thing we do is we digital write to the same pin and we tell it go low or turn off. And then we delay again for 1 second so the eyeball can see that it turned off. We loop back up to the top, we turn it back on, we delay, we turn it off, we delay, we loop back up, we turn it on, we delay, we turn it off, we delay. Everybody understand what we're doing here?
Jim, where's the start of your do loop? Is it with the right-hand parentheses?
Say that again, please.
Okay, down below, right below the pin mode statement in your
All right,
code.
right here.
Yeah, is the next line the beginning of your do loop?
Oh, no, this line is the
Yeah.
end. This line is the end of the setup loop.
Okay, so then the next line with the double hash marks is the beginning of your do loop.
That is a comment, okay? That's written there just to tell us what's about to happen. Okay, so it says the loop function runs over and over again forever. The next line down where it says loop, that's the beginning of the loop. Okay.
I guess my question is, where do you define the end of the loop? At the delay 1,000 statement at the very bottom?
Okay. Everything between the braces. See where I've got the cursor on the brace right there? That's the beginning.
Okay, I'm sorry. The bottom one looked like a parentheses. It's actually a brace. That's what I was. Okay, I understand where your do loop is there. That's fine. Thank you.
You're welcome.
And Jim, another question. Is there a limit to how many seconds you can have that delay?
No, sir. Well, actually there is. It's the amount of milliseconds that you can hold in a long data type, but that's out into the millions of milliseconds. We're not gonna. I'm gonna go over data types a little bit here. Matter of fact, why don't I just do it now? Since you brought up the question, it's a good natural time to do it. How many of you have heard the old real estate statement? What's the most important thing about real estate? Location, 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 right? Well, the most important thing in a computer is location, location, location. Because all you're doing in a computer is playing with memory, putting stuff in memory, taking stuff out of memory, moving it around. So you have to know where it's at. The way the computer does that is by defining data types. Now there's two types of data. One is referred to generically as a variable. That's something that changes. Okay, another thing that you have is a constant. That's something that remains the same. It never changes, right? And you'll see me develop those thoughts a little bit as we come down the page here. The smallest piece of memory that you can access is called a bit, okay? You can think of this as one input terminal or one output terminal. When you're playing with an input or an output, you're manipulating a bit. The next generally accepted data type is the byte. This is 8 bits, all linked together and looked at as one entity, okay? It's often referred to as a character, but that's really a sloppy way to talk about it, because some languages use character as a data type. A little bit of interesting history here. The byte was developed by IBM, and to them it was a software thing, and it was 7 bits, not 8. Because with 7 bits, you can define all the keystrokes on an ASCII keyboard, with the exception of special characters. So the byte was developed to store ASCII characters that represent the keyboard. Hardware came along and made an 8-bit chip, and they snatched up the term byte. And so now you'll hear the byte referred to as 8 bits, and that's being a hardware term. The next thing that you'll hear in a computer is the word, okay? And you've heard people talk about, I have a 32-bit computer, okay? What they're telling you is that's the largest chunk of memory that my processor can talk to with one instruction. That's a word, okay? Other machines will say, I can talk to 64 bits. I have a 64-bit machine. That means at one time, the instruction can look at 64 bits. That's a word. Now you can see that the more bits you can talk to with one instruction, the more power you have. That's why we keep upgrading our computers from a 16-bit machine to a 32-bit machine to a 64-bit machine. There's 128-bit machines out there now. There are much bigger machines, okay? But the word, therefore, is not defined by the number of bits. It's just defined by the largest amount of memory the computer can talk to at one time. So let's look at these data types. We have bool, B-O-O-L, which is Boolean. That's 1 bit. And it can either be on or off. It's either true or false. That's the way we look at our output pin. Okay, it's either on or off. So we're manipulating a bit. Okay. The next one up is the integer, int. That's a whole number. Okay, no decimal points with an integer, right? And it's 6 in this machine. In the Arduino, it handles integers with 16 bits or 2 bytes. But an integer can be a plus or minus value. So you can have negative integers, okay? Here's an example. If you wanted to declare an integer, you would tell it, I want to use an integer, int. This is the name of my integer, and I can set the value to whatever value I want it to be, equals 0. And you'll see this a lot in the program. That's called preconditioning a variable to a known value to start with, okay? The next data type is a real. long, which in numbers is a real. And that means it can contain a decimal point. So these numbers can have a fraction, if you will. Arduino uses 32 bits or 4 bytes to define a real, and it can be a plus or a minus value. If you want to declare a real, you say, I want to use a long. This is the name of my long, and this is the value I want to preset it to. Okay, the next one down, a little bit more complicated. It's an array. Okay, now I'm going to use arrays in my programs. So I want you to take a look at this a little close. Okay, an array can be any size. And that means they can grow and shrink, grow and shrink, grow and shrink as we need them. The way you can tell an array real quick is to look for the square brackets. If you see the name of a variable with square brackets after it, you should automatically think, oh, this is an array. And what can an array do for us? An array lets us group together a series of different datas. So we can have an array of integers, an array of long, right, or array of bits, okay, and we group them together. And that makes them easier to deal with. Now, the way you access an array is with an index. So you'll see the bracket with a number in it, 0, 1, 2, 3, and so forth, okay? Now, let's illustrate how we use that. We'll define an array. We'll say we want this to be integers. We want it to contain integers. This is the name of my array. And this is the number of elements that I want to stuff in that array. And then I say equals, and over here inside of my curly braces, I put 1, 2, 3. Okay, now when I want to talk to one of these values, I would say my array 0. Okay, because 0 is a real number to a computer. So 0 looks at the first index. The value stored there is 0, right? So, and then if I say my array bracket 1, it looks at the next one, which is 1. My array 2 looks at the third one. So that's how you get to the individual values stuffed in that array. Now, the last thing to look at here, I told you we had two types. We had variables and we had constants. Everything you've seen me declaring in here so far has been a variable. Okay, now I want to show you how to declare a constant. So you put the abbreviation constant here, and then you tell it the data type. So it can be a constant integer, constant long, whatever data type you need. And then you name it, LED_count equals 6. So now anywhere in the program where I use the word LED_count, the computer knows that I'm really using the number 6. Why do this? Because we program now at the logical level, not at the hardware level. So we want to make it easier for us to think on the logic level instead of trying to remember, oh, I want to talk to the third one, or no, I want to talk to the fourth one. We give them names that mean things to us. It makes it easier for us to program. Okay, so now that we've kind of seen the data types, we'll go back and pick up where we were. Does this LED built-in make more sense to you now? That's a constant. I didn't define that. The basic programming language defined that for me. I'm just allowed to use it, okay? So that's always talking to the LED built-in. The power of this is that since it's in the compiler, when I use LED built-in, no matter which Arduino chip I'm using, it points to the right one. In our case, it points to 13. On other boards, it's going to point to pin number 6. But we don't have to worry about that. All we have to remember is we want to use the built-in LED, and it takes care of what pin to go to for us. So with that done, let's see it operate here. Let's go back over here. It'll get better, guys, I promise. Are you seeing my breadboard?
Yeah, we see your breadboard, Jim.
Great, because I'm still seeing you guys, but that's good. Let me pull this out of the way, and now I'm going to plug my circuit in. Can you see my
Could you zoom, Jim? Could you zoom your camera on the breadboard in just a little? It's a little hard to see what you're doing.
Yeah, I've got a white glare on it. I know. I've tried to shield the light and everything. It's the best I can really do. I turn it up.
No. I mean, bring it in a little bit more. We can't really see what you're doing on the board level. We need a little bit closer view, if you could.
Let me see if I can pick it up and set it up on this box. Any better?
It's a little better. We're having it's difficult to see the individual components. We can see the Uno, we can see the breadboard, but the rest of it's kind of a blur.
Yeah, does that help?
It's better.
Okay. I have the LED. This wire comes over to my ground connection, so that this bus is ground along here now. The LED to one row of 5 chips, through the resistor to the other row of 5 chips, the red lead over to my pin 13. Now I'm going to plug it in and turn it on. Can you see the 2 LEDs blinking?
One on the board and the
Yeah.
one on the breadboard.
Yeah, one on the board, right? That's the built-in LED on pin 13. And then we plugged into pin 13 and brought that same signal out to an external LED on our breadboard. And so you see them blinking simultaneously because they're being turned on and off at the same time. Okay, now I'm going to leave that there for a second, and I'm going to demonstrate. You're not going to see this, but I'm going into my delay. I'm going to let me let you see this so you can see how to download it too. I'm going to go back into my code, and where I have the delay, I'm going to change that from 1,000 to 500. To 500. Then I'm going to, here I can check my code, verify it. If you look there in the screen right here, it says verify. The next one says upload. Okay. This one says save it to my computer. So that's what these little shortcut buttons are doing. So when I tell it to upload, before it does an upload, it will automatically verify my code to see if my changes are correct. So I'm going to click upload. Down here you see it says compiling sketch. Now it says uploading and done uploading. All right. So that change was sent out to my Arduino board. So let's go back and see what it's doing. Can you see it blink now? You see it? You see my breadboard blinking?
Yeah, both of them are blinking. They're blinking at the half-second basis, which is what you put in.
Can you see that they're actually blinking faster, right? On off at a faster rate. So that's how you can control the speed of an LED, how to turn it on and off at a faster rate. So let me drop out of my screen share again. Okay, come on. I can't get my little board to come up here to tell me to drop out of screen share. All right. You have to give me a second, guys. My my little screen share thing won't come down for me. So I'm having a hard time here. I don't know why it's locked up on me. Can you guys still hear me and everything?
Yep.
Yes, we
Okay.
can.
Yes.
There we go. I got a live fill that time. I don't know why I can't get to my screen. All right. So that's our simple little blink circuit. Anybody have any questions about that? How that works or what I've shown you? All right, I'm gonna move over to my next example. This one gets a little bit more involved. Let me show you how I got it, where I got it from. I went on the internet and I just did a little search. I said, hey, who's written a little program for random blinking lights? And by golly, here's a guy that did it, okay? And this is what his looks like when you run it. So he's randomly blinking lights. And I said, okay, that's nice. But I came down here and looked at his code. And he's proud of this code, and he should be. He's saying, hey, look, I did all this in 9 lines of code. Oh-wee, that's great. But can you understand his code? I can, but it took some time. I had to stop and study it. I don't want you guys I don't want you to have a brain fart and get confused. So I'm not going to use his code. I'm just letting you know this is where I started from, okay? And here at the top, see that in it? That's an array, right? See the square brackets? And he used a 6 in there. So I took his idea of an array and I used it, okay? But I changed the rest of this down here. But I just want you to know this is the base from which I got my idea. Okay, so I want to give him credit for where I got the idea from. So let's take a look at what I did. And I'm going to open, and there's my random. So I'm going to open my random code. And since we're done with blank, I'll get rid of it. And I'm not saving the changes. All right, now I wrote my code a little differently here. First, I want you to note my comment area down here. I tried to write this code for a non-programmer so that other people could use it instead of writing it for programmers. And so what I tell you here is set everything above these lines and you don't need to change any code. So if you just play with the stuff above this comment, download it to the Arduino, you can make changes without having to play with the code. So that's what I mean by I wrote it for non-programmers. I put all the variables and all the controls right here at the top, and I tell you what they do. And then even if you don't really understand what's happening down through here, you can use the code, okay? So I tried to make it practical for you guys. So let's go through here. Let's see what I've done. First thing I did was I set the total number of LEDs, okay? So I said, this is a constant, it's an integer, and the name is LED count, and it's equal to 6. So I'm gonna play with 6 LEDs. Pins that LEDs are hooked to, okay? This is these are going to be integers, LEDs, LED count equals 8, 9, 10, 11, 12, 13. These are the pins that I'm going to hook the LEDs to. Okay, and the reason these are digital output pins, okay? Then I say keep track if the LED met the set time value. What I'm doing here is down below, I'm going to let you insert the amount of time you want these LEDs to blink at. And then I have to test it to see if it met that time requirement. So I have to remember which LED has been tested. Okay, set LED initial state on, off, high, low at startup. Okay, so in here, this is a Boolean state. It's got brackets, so it's an array. LED count. And then I say, okay, the first LED I want it high or turned on, low or turned off on the second one, high on the third, high on the fourth, low on the fifth, and low on the sixth. So now I can go in there and I can play with high, low, high, low, high, low, and I can set the startup pattern to whatever I want it to be. Okay. Set the toggle time for each LED in milliseconds. Okay, again, this is an unsigned long. That's its data type. It means it can hold a huge amount of, huge number. Okay, let's just leave it at that. And then I set the time that I want each LED to cycle through a blink. So the first one is going to blink at 1200 milliseconds. So it's going to be, the first LED will be on for 1.2 seconds, off for 1.2 seconds, on for 1.2, off for 1.2. The second one will be on for 2.5 seconds. The third is 9 seconds. The fourth is 4.2 seconds, 5.5 seconds, and 8 seconds. So here you can go in and you can set how long you want each LED to blink, okay? Then this is a must. Must be set larger than the largest set time value. So the largest set time value is right here, is 9,000, okay? So then I set the cycle to 9,100. Why? Because I have to be in my test loop long enough to have seen all of my LEDs blink before I reset and start over. So that's the only tricky part really right here, is remembering to set this higher than the highest number in here, okay? Now I'm going to come down here. I'm going to do a preset. I use 2 do while loops, okay? Now, do while is again, I went to the Arduino site. Actually, what I did, it's even simpler than that. I just went to Google and I said, Google, what's a do while loop? What's an Arduino do while loop? Boom, and it came to this page, okay? So it's that simple to get help, okay? And a do while just explains that it starts with the word do, and it ends, and do followed by a curly brace, okay? And it ends at a curly brace, and everything in between gets done while this condition is true. So I can put do, and then I come down here and I say while Jim Kelly is speaking. And everything inside that loop gets done while Jim Kelly is speaking. But as soon as Gregory starts to talk, I drop out of that loop because Jim Kelly's not speaking anymore. Make sense? So we're testing at the bottom and not at the top. So the code gets done once regardless, and then it gets tested to see if it should do it again. So then we're just going to run around and around inside that loop as long as this while statement is true. Once it gets false, bingo, we drop down to the next line in our code. Okay, so we'll drop back to our code. And I say right here, lost my spot. Preset, oh, okay. I preset my, my loop with I equals 0, okay? So we'll get back to the loop in a minute. I'll show it to you. Then I define unsigned long previous which means previous milliseconds. So I preset this to 0, and I look at the current milliseconds. I set that to 0 as well. So those are my two variables that I'm going to use to track my time. Then I go into my setup mode. So here's my curly bracket. Here's my ending bracket. So everything in between gets done just one time at startup. So here I do a for loop, okay? For loops are not too difficult. Let's take a quick look at it again. For the initialization condition increment. Now that doesn't mean a whole lot to you yet, okay? But I want you to see how it's laid out. And then again, see, here's the curly bracket, and here's the ending curly brace. So everything between these two braces will get done as long as this condition is true. Okay, this one gives us a control over the condition. This one is the initial value that we're going to test against. So let's go look at our code and see how we fill that in. So our initialization, we're going to use an integer called I. We're going to set it equal to 0. And then our condition, see the semicolon? It separates this element from this element, okay? So now our test condition says, as long as I is less than LED count. Remember at the top of the page, I set LED count to equal 6. Now, I use that constant down here, right? LED count. So as long as I is less than 6, do all the stuff between this curly Q and this curly Q. Okay? So it's at 0 when we start. So is 0 less than 6? That's true. So drop in and use the pin mode function to set LED 0 to an output pin. Okay? And delay the whole program for 10 milliseconds just to let things breathe. Then it comes back up. This element now increments. This is shorthand. This means I is now equal to I plus 1. That's the programming shorthand for I equals I plus 1. Okay, so what this does is it now changes I from 0 to 1. Is 1 less than 6? Yes. So now it drops in, uses pin mode again, goes to the LED array, but this time it's looking at element 1 and sets it to an output. So I'm going over 6 times, I'm going over the pin mode operation, and I'm looking at each of my pins and I'm setting them to an output. Okay, now another way I could have done this was 6 lines of code. Pin mode 8 equals an output, pin mode 9 equals an output, and I could have set those pins directly. But this is the proper way to do it in programming. The next thing I do is another for loop, and I set all my LEDs to the state. Remember the state array above was, when we start, do we want it turned on or do we want it turned off? And so here I'm going to go over the 6 LEDs and I'm going to compare it to the state, and I'm going to either turn it on or turn it off to match how you told me to use them up above. Here I'm going to start my serial, serial is a communications bus, and I'm using it here under my tools. Here's my serial monitor, and I'll be able to monitor what I'm doing here. I'll let you see that in a minute. I have to set up my hardware first. But now I've got everything preconditioned. Okay, so here's my loop. I begin in my loop. Okay, there's my curly brackets for the beginning of my loop. Now way, way, way down here at the very bottom of my program, there's the matching curly brace for that loop. So everything inside my program is in that do loop. Okay. So I just continuously repeat this code. The first thing I'm going to do in there is I'm going to set my test, okay, to have I tested my LEDs? I'm going to set them all to 0. No, I have not tested them, okay? So I drop in, I set all my tests to 0s. Here's my do while loop. See that do statement? And way, way, way down here towards the bottom, here's my while statement. And I'm going to do that while the current amount of milliseconds minus the previous milliseconds, which I've saved, and you'll see that in a little bit, okay, is less than the cycle. Now, remember, way back up here when we define things, remember I told you cycle has to be set longer than the longest time I want to control an LED. So as long as my program is run less time than it takes for all my LEDs to blink once, I want to keep doing it to make sure that I get all of them to blink. Okay. And then the next thing I do, which is confusing, is I put that do inside of another do. Okay. And the test statement for that do is right here, while I is less than the LED count. Remember, LED count is 6 because I'm looking at 6 LEDs. So I've got a do inside of a do. So I got 2 loops going. Okay. I know it's confusing. I'm not going to try to make you master it. And I'm going to stop trying to explain the code at this point and just summarize what you're going to see. Okay. Because I can see the glaze in your eyes. Okay. I can see that glaze. We've got this code. Anybody that wants to go deeper, call me and I'll go line by line over my code with you and explain it. It's available. You can download it and just plug it into an Arduino and use it. Okay. You don't even have to understand it. So let me stop here and stop my share there so you can see what's going on. I'm going to change out my breadboard over here. Okay, I've got one lead that I've got to hook to ground. Let me disturb you here for a second. I got to go back up to the top of my code here. Pins 8, 9, 10, 11, 12, and 13. Okay, so this LED is going to go to pin 8. Nine, 10, 11, 12. $13. All right, do you see the white LED blinking there? Eight, nine,
Yeah, we can
10.
see it, Jim.
I got myself, I'm in the dark here where I can hardly see. 8, 9, 10, 11, 12. Okay, I believe I got them all right. Now, I'm going to download my code. Okay, so here's my random, and I'm going to tell it to upload my code. I'm sorry I keep using that wrong terminology, guys. On this one, it's upload. Okay. So here at the bottom, you can see it's compiling my code, and now it uploaded it. Okay. Now let me stop my share. Can you see my breadboard? Can you see my breadboard?
We can see different LEDs going
Yeah.
on. Yes.
Okay. You see they're turning on and off at different rates. Okay, that's because I've got them on different timing circuits. So with this code, I'm controlling 6 LEDs, but I'm telling them to turn on and off at a random pattern with different timing circuits, so that they're not all on for the same amount of time. Some are on long, some are on short. So my thinking here is if you had an apartment building or something like that, and you wanted to put LEDs in the windows where people are coming and going through rooms, you might want to turn them on and off in a random pattern, right? Somebody came in to find their glasses, turn it off. Somebody went to the refrigerator, turned on the light, turned it off when they left. So this is the concept that I'm trying to get across with this code. Everybody see that? Okay. So that's the power of using this microprocessor with LEDs instead of hardwiring to direct to a power source. You can set these LEDs up to do different things at different times. If you put it in the building and you find out, oh, I don't like the way it works, you can just plug into the processing chip, change the pattern again. Okay? And you don't have to do any rewiring or anything. That's the power of putting that microprocessor in the circuit. Now, I could go back in. I can go back into this code and come all the way back up here to the top. Okay. And right here, this is my set time, right? That's how long these LEDs are going to stay on and blink. So I could change these. So I could change this from 1200 to 500. Let's drop these down to 600, 700, 800, 900. And we'll let this one blink for a full second. You can see the time that they're going to be on and the time they're going to be off now is much shorter, isn't it? So they're going to blink faster. So now this longest time I've got is 1,000. So I can come down here and I can change this to be 1,100. Okay, it's just got to be a slight bit longer than the blink time. So now that I've done that, I'll upload that code. Now let me stop my share. Can you see them blink now? They're blinking at a much faster rate, aren't they?
Yes.
Okay. And so there I've adjusted the time on how long each one of them blinks. So I can play the game, you know, with a lot of different LEDs and get the patterns that I like. Okay, now real quickly, and without going again, without trying to kill you with the code, because I know I've hit you with a lot of it already. I'm going to show you how to do this where you can dim the LEDs. Not only turn them on and off, but how you can turn them on and off and set them at different brightnesses. So give me a second, guys, and I'm going to change camera so maybe you can see my pretty face for a minute here. Well, I thought I did. You guys see me now? Okay. Give me a minute to change out my hardware here. Oh, come on. I'm having a hard time seeing, guys. I found it. Guys, I apologize. I'm having a hard time here. I tried to set this up so I could see it. I'm going to have to pull down my shield. I set all this up in bright light. Now I can't see it in the dark, so I have to cheat, pull that down. I'm almost there, guys. I've just got one wire crossed here. Okay, guys, I have to apologize. I wish I had more Arduinos to hook these things up to get this program started. I'm having difficulty. I can't get my wires here where they belong. Now I think I got them. Now I think I got them, guys. Good. Sorry for that delay. I couldn't see in the dark, and I got my wires crossed and I had to straighten them out. Now let me go back to screen share. I'm going to get my file. I'm going to use the pulse width modulator card.
Jim, you need to put your mic back on.
I'm going to show you one. Real quick. Here's the commercial too. you want to know where to get this starter kit, you can go to this link up here. You can freeze this and look at it. Right? So that's where you get the starter kit and everything that's in it. This is a pulse width modulator card. It costs $3.59 plus shipping. Okay, so what? $3.50 going to cost you less than $10. Okay, and it controls 16 servo motors, 16 LEDs, whatever you want to do with it. Okay, and we use pulse width modulating to fool the device that's hooked to it to think that it's running on an analog signal. I told you earlier I was going to show you what that's all about. So let me go back here and call up my next slide. Don't let it scare you. Okay. Start over here in the far left. This is an analog signal. You see the zero reference? Analog means it's a constantly changing value. Okay, so we usually see that with an AC wave sign. So we go from 0 up to a peak, down to 0, reverse and go negative to a peak, down to 0, up to a positive peak, down to 0, negative. You see how that works. That's an analog. Okay. The next one down here is a digital signal. Digital is 2 states, on or off. So here at this point, we turn it, whoops, hit the wrong button there, guys. We turn it on, it rises it instantly to its max value and stays there as long as we leave it on. Then we turn it off and it drops back to 0, stays there as long as we leave it off. Up, on, and off, on, off, on. But the voltage is always the same, right? So that's digital. And we control the on-off with a clock rate. We won't go too deep in that. It's just the frequency at which we want to turn it on and off, on and off, on and off. We set that. We can control that. So looking at that, we can come down here and look at this digital signal. See here, I'm coming along at 0 time, 0 voltage, and I turn it on for 1 clock. I turn it off for 1 clock. I turn it on for 2 clocks. I turn it off. I turn it for 1 clock. I turn it on for 1 clock and off. So you see I've created a different pattern here. Now, that gives me a way to represent things. So the one on for 1 clock may represent a 0. On for 2 clocks represents a 1. Okay, and off, on again for 0. So now I can send 0s and 1s across wires, and the other end can see them as 0s and 1s. It's just to give you an idea how things communicate. Now over here, this is the big boy. All right, this is the one that's kind of confusing. Our baseline is time. Our vertical line is amplitude or voltage. Okay, here's an analog signal that we want to reproduce. Well, we can't vary the voltage with precision, but we fool the output device. So what we do is we turn on our digital and leave it on for a period of time, turn it off, or we can increase its output like so, and then decrease the output level. We do that with setting the duration of the time that we want it on and off. So we can stop this pulse. See, this pulse goes from 0 all the way to maximum, but we can actually control the amplitude of this pulse as well. So we can turn it on and turn it off maybe at the halfway point, so that it only sees half the voltage. Okay, it never gets to the full voltage. So we can play with this amplitude. And by doing that, we can reproduce things such as music, human voice, and a speaker sees it as an analog signal that it requires to work. And so we fool the device into thinking that it's seeing an analog voltage when it's really seeing a digital voltage. So this is what we do with our LEDs. We're going to come in here now and we're going to decide when we turn it on and when we turn it off. Okay, and I just want you to kind of understand this is what I'm doing, right? So I'm deciding how long to turn it on and when to turn it on. Okay, like this at this point, I don't turn it on until I get to this point. Then I turn it on, right? So it's just a matter of how I want to control it. And it's not that difficult to actually control and see the effects that you want on your LED. So with that said, let's go back and play with this a little bit. These are great little devices. 4 wires. You can't. It keeps bouncing on me. But on these pins up here, these connect to the Arduino, and it talks over a communications bus called I²C. And I know that makes a lot of sense to you. I'm not going to try to explain it, but the board talks to this board and tells it what to do. And there's a processing chip on this board that hears it and then controls these output pins and sets it as it's instructed. Very nice little board, 16 outputs. And it's designed to be for servo motors to be plugged directly into. So the wire that comes with the servo motor just plugs right into it. Makes it real easy. Makes it easy to plug an LED into too. So with that, let me flip cameras for a minute. Stop my share. Wish there was a way to do that without having to stop the share all the time. Okay, can you see my breadboard? I see a shaking head. Okay, so here you can see the hardware. I've got my 4 wires plugged in to my Arduino. 2 of them, these 2 wires over here, are my IC² communications bus talking to that card. The other 3 wires going to it are power. I have ground going to it. I have plus 5 volts going to it, and a second plus 5 volts going to it. I'm borrowing voltage from the Arduino to drive the output pins by that second voltage. If I need a heavier voltage and heavier current, I leave that second wire off and I plug in on this terminal strip over here. I put my 5 volts, external 5 volts in here, and that drives the output pin power. Okay, so that's where you would have to plug in to do your servos. LEDs, you can just use it this way. So, having shown you the hardware hookup, the rest of it looks pretty much the same, doesn't it? 6 wires out to the board, 6 resistors, 6 LEDs. The difference is that I've moved on my pins. Let me go back to my screen share again. This time, see, instead of using pins 8, 9, 10, 11, and 12, which are digital pins, I moved my wires from there over to pins 14, 15, 16, 17, 18, and 19, or analog 0, analog 1, analog 2, 3, 4, and 5. So I've moved my wires to the analog outputs. That lets me play with my voltage levels. Okay, so put that down. Here's my code. And this code is very similar to the code I showed you for just the blinking of the LEDs. But I added in a brightness control. And again, I didn't want it to be, oops, yeah, I didn't want it to be something you couldn't use. So I've set it up so you can plug the values in at the top, and away you run with it again. Okay, so I'm going to download that or upload that into my brain. Compiling error occurred while uploading the sketch. What did I do wrong? Can't set column state 4. Okay. It's got timeout on me, guys. When I unplugged it, plugged it back in, and my COM ports got confused on me. So I'm having to, I'll have the simplest way is to kill it, restart it. Now let me see what COM port it picked up. It used to be on COM port 4. I'll explain what I'm doing here, guys, as soon as I get it resolved. Let's see what COM port went away. This is much more fun in the classroom where you can actually do it. All right, it uploaded. What happened, guys, when I unplugged my board to bring it over into light, trying to plug the wires in, is it opened up the COM link, and when I plugged it back in, it couldn't find it and reconnect to it. So I had to shut things down and reconnect. Okay, so let me show you what I've got going over here. The basis of my code is that I've linked the 6 LEDs by predetermined times, but I also allow you to set the brightness of the LEDs at the top of the code. Okay, see here. This is not the oh, come on. Come on. Open the wrong code on you guys. Okay, now it's downloaded. Now I can actually show you what I was trying to find. Again, at the top of the code, I have that same statement. You don't have to play with anything below this point. Just play with the stuff up above. And you can see that it looks a lot like the last one, right? You get to tell me how many LEDs you're using, 6. Okay. What pins are you going to put them on? Okay. And the test, I preconditioned the test loop to 0. You get to tell me at startup which ones you want high and which ones you want low. And then you get to tell me here how bright you want that LED to be. Okay. So I can change the brightness. And then how dim do you want it to go to? Okay. So I can go from a bright setting to a dim setting. And how long do you want each one to blink? So it's very similar. I just added in a couple more items there. How long you can blink it. So I've got it downloaded. I said I do. It says let me compile it and run it again. It's doing everything but blinking for me. It's downloaded. I got a wire across. I'm gonna download this code for a second. This is a simpler code where I just blink them. Okay, that code works. Can you see my breadboard? Got a wire that keeps popping loose on me. There we go. Can you see that breadboard?
It's hard to see with the glare, but you can tell that
I
they're
see
blinking.
your lips, but I'm not hearing anybody talk.
Yeah, can you hear me, Jim?
Did you mute yourself? Yeah, you're muted.
No, I'm unmuted, but I think he might have muted everybody. I don't know.
You need to put on your headphones and use your microphone again.
Okay, guys, I've lost all of you. Okay, Chuck, thank you. Silly me, I forgot my headset. Okay.
Yeah, as I was saying, Jim, we can see the breadboard, but there's glare, so we can see the lights blinking, but it's hard to tell they've been dimmed.
Yeah,
But we get the idea. I think.
yeah. I'm
Right.
sorry, guys. I got
You might try turning off the light in the room.
yeah. If I do that, okay, hang on. I'll do that, but that caused me troubles when I was trying to hook things up. But I'm sure you can see them better now.
Yeah, and you can see the different intensities as well.
Okay, so that pulse width modulator card lets me go in and adjust the amount of time that I turn on that output. And when I do that, that to the human eye looks like a duller light switch because it's on less. Okay, so I vary the brightness by doing that. Now let me see if I can get that other code to load. Well, it loaded, but it's not doing what I expected it to do. It froze on me. I don't know what's wrong with that code. It worked for me all week. And then this week, you know, now that I wanted it, it fails. All right, guys, so I've got code and it's available for all of you if you want to download it and use it to, you know, to blink LEDs and put them in your buildings. I would suggest using the Nano. It's much smaller. And of course, I'm available when you load that code. Looks like Scott dropped out on me for a minute there.
I'm here.
Okay.
Hey, Jim, the kit you were advertising there, does that have a Nano in it or just the standard Arduino?
It has the Uno. It comes with the Uno,
Okay, not the Nano.
not the Nano.
Okay.
The Uno that comes in the kit is designed for the kit because on the pins it has the female sockets for these nice little wire connections.
I got you.
So you can plug
Okay.
it right to the breadboard. The Nano comes expecting to be plugged into a circuit board, but they make a breakout board for the Nano. It costs you about $5-6, and you plug the Nano into that breakout board, and then you get the nice, pretty little jumper pins that you can use for testing. So it's one more step involved in using that Nano, but I do believe because of its size that it will fit into the buildings better and do what we want to do. I know I got heavy into the code. I tried to stay light, but if you're going to use the Arduino, you know, you need to get into the code a little bit. But remember, you know more than you thought you did. Just start with the thought, it's a recipe. First, I have to tell it everything I'm going to use by defining it. Then I have to give it the instructions on how I want it to use the items. Okay, that's the basic thought process. With time, all the little instructions become natural to you. It's just like almost like speaking English. There's an if statement. Okay, you tell your son, go to the refrigerator and get me a beer. If it's hot, bring me a Coke. So you put a condition on the if, didn't you? See, and that's exactly kind of the way you talk to the computer. So if the beer is cold, you do that. If not, then you grab the Coke. Okay, so it's the same idea when you're talking to the computer. It's practice. I can sit here and show you this and maybe stir an interest. You need that kit to get your hands on and get things started. So let me.
Hey, Jim, can you show that kit again?
Pardon?
Can you show that kit again?
Sure will.
The
You
box that it's,
want me to show where to get it, or?
Well, wasn't that banggood.com?
Yeah, I'll put
Okay.
that back up for you.
I was just wondering what that kit was, you know, model number or something. The starter kit is what I was more
Yeah.
interested in.
Okay, there it is.
Okay. I'm trying to scribble this down. Geek.
Yeah, if you wait a day or two, I'll post this video, and then you can just freeze the screen and get all this too.
Okay. Well, I
Okay.
think if I go to that website,
Yeah,
I've seen these kits before ranging anywhere from, this is the cheapest I've ever seen the price on them. Some of them
Yeah,
go up to $50 or something.
yeah. If you're not careful, you know, you're going to end up buying a much more expensive one,
Mm-hmm.
right? But this is the cheapest one I found, and it's a good kit.
Well, I can see it's got a servo in there and then another motor.
You had a little DC motor to control. Okay, and it comes with a variety of resistors. And there's the Uno. You see the little black strips along there?
Yes.
Right, that's where you plug these wires in. See the little tips of the wires?
Yeah, the jumper wires.
Yeah, you plug them in there, and then you plug them into the breadboard wherever you want them. So that it's a nice, easy kit. You don't have to do any soldering. It comes with everything you need. So your group of LEDs, okay? A servo motor, a DC motor, even comes with displays. So you can learn how to write hello world.
So you got back in time to watch that, huh?
Well, I just turned it on just a minute ago.
Oh.
Okay, and see, this is a remote
Listen,
control
Myra,
right here.
Two brothers.
Okay, so
Johnny?
you can learn how to use an infrared
I bought a ticket.
sensor, and you can
Okay.
use it as a remote control, and you can make different things happen in the Arduino based on what that infrared sensor sees.
Yeah.
So
Does it have like a model number? Like if I go to that website, this UNO.
Yeah, if you
R3?
go Uno basic starter kit, just go Banggood right in front of it and just go Uno basic starter kit, and you
Okay.
should be able to find this page.
Okay, that looks like a good deal there.
Yeah.
Hey, Jim, it looks like there's a 9-volt battery connector there in the middle.
Yes.
But so I don't see a 5-volt power supply.
The Uno will work off of 9 volts. Okay.
Oh, it does.
Yeah, you can plug it in. It has a regulator on it, so
Okay.
so
Okay.
it'll drop it down.
All right. Could you put up the that other board
The
off the Banggood site, the one with the for the pulse width?
this is the pulse width modulator, and this is the PCA 9685. If you just write that number down, that say Banggood, and that number, you should come to a link to get to this screen. Okay, there'll be a lot of others too, but this Banggood is about the cheapest. I'm going to share. Pardon, go ahead.
Is that where you normally buy your electronic supplies?
It varies depending on what I'm buying. Okay, when I'm buying for my electronics boards, I buy from a different company just for convenience, because they're linked into the same program that I design my electronic cards on. So, but if I'm not doing that, I usually go to Banggood. I want to share another one with you that a lot of people have talked about. Everybody says, hey, do I have to use a resistor with my LEDs? And the answer is not necessarily. Okay, it depends on what you supply it with. So this little board here is called a DC to DC voltage regulator. And it's a step-down power supply. And what that means is you can put a high voltage in and it will drop it down to a lower voltage. It won't take a low voltage in and raise it to a higher voltage. It won't do that. It's a step-down device, okay? So if I come over here on this pin, it's a little hard to see. Maybe I can get another shot of it. Yeah, here. This is a good one. Okay. Oh, come on. See, on this terminal strip, it's marked N plus and N minus. So if you put your power supply in here, you can bring it out on the opposite side where it says out minus and out plus. The secret is that brass screw that you see right up here at the top. See that brass screw? This one comes with a built-in meter that shows you the voltage that's going out. So you turn that screw until you see 3 volts on that meter. Then if you do that, then this output has 3 volts on it, and you can drive your LEDs with no resistors. Okay, so that's a nice little thing. If you've got a series of buildings and maybe you've got a little city, right? You can get up to 2 amps of current at 3 volts there. So that'll drive a whole lot of LEDs. Okay, no resistors. You can get them cheaper. This one is $3.22. You can get them down to like $1.95 if you buy it without the little built-in meter. Okay, so if you want to go cheap, you can do that, and then you put your own voltmeter across the output and turn that brass screw until it reads 3 volts. And it does the exact same thing as this expensive card. Okay, so it depends on how much money you want to spend.
Now the input voltage can be over 12 volts?
Yes, sir. If you scroll these pages down, a lot of people like to stop right here because these are frequently bought items, and they go, oh, I don't want any of that stuff. But if you continue to scroll below, it gives you the specifications for that board. Okay, and it tells you it can be like 24 volts. Let me see if I can find it.
I was just wondering what the maximum voltage
here it is. Input voltage can be anything from 4 to 40 volts.
Okay.
Okay. And the output is adjustable in the range of 1.25 volts to 37 volts. There's a power loss for using the module. So you can't put 12 volts in and get 12 volts out. Okay. You'll always get something less because you're consuming some power to use the card. Okay. So you can almost get the full voltage out, but it's going to be. Go ahead.
Do you have experience with this module?
Yes, sir. I use them all the time.
I'm just curious if as you change, let's say you set it for 3 volts.
Yeah.
As you change the output loading, does the module regulate to keep that output consistent at 3 volts?
No, I don't believe there's a lot of regulation on that card, but I've not had it drift off very much.
Okay.
Because it's rated to handle up to 2 amps. Okay. At 3 volts. So it doesn't drift much. Okay. And if you're worried about that, the way you do that, and this is how you do a computer bus as well. What you do is you wire in your all your string of LEDs. You find the LED at the far end of the last one that you wired, and you put your voltmeter across that LED. And if it's reading like 2.3 volts, then you leave your voltmeter there, but you go back with your screwdriver and get on that brass, and you adjust that until that last LED see something like 2.8 volts, okay? This meter over here may read 3.2 volts, okay? But that's okay. You're still within the range of the LEDs, but that last one will brighten up a little bit. Does that make sense?
Are you talking about LEDs that are in parallel then?
Yeah, they're in parallel.
Okay, so the last one on the string in a parallel circuit.
Yeah.
Okay,
You can parallel them because you don't need resistors now. Okay.
because of, I guess, what, line loss and other things?
Yeah, you'll get a little line loss, and each LED will draw a little bit more. You've got the fluctuations. Okay, you won't get
Okay.
much. Okay, the only thing I would say is hook them up at 3. Set it to 3 volts. Hook up your LEDs. If they don't quite meet the brightness that you want, tweak that output to 3.1, 3.2. See if they brighten up a little bit for you. Okay, you can get away with a little bit over 3 volts. Okay? A lot of LEDs are actually designed to work at 3.3 volts. So that's where your data sheet comes in. When you buy your LEDs, you look at that data sheet to find out what that LED is supposed to work at. Okay, because the next manufacturer, if you go to a different site and buy a different LED from them, it may be different because it's manufactured by somebody else. So voltage varies a little bit between LEDs, but they'll all work within a range. If you work with 3 volts and 20 milliamps, you're good as gold on on almost every LED that you ever get. Okay, so just start with that, but then you can, like I said, you can tweak that output, get a little brighter if you want them, a little dimmer if you need them dimmer. Okay, of course they're not going to twinkle or blink. They're all just going to come on and be at the same level constantly, right? So
I got a question.
Yeah, go ahead, Scott.
A lot of times I'll use a 9-volt battery to power the LEDs in the structure. And I set it up where it can be on a 12 volt with resistors for a 12 volt.
Yes.
If this changes from 9 volts to 12 volts, does the output change from 3 volts to a higher voltage? Or does it still stay at that setting?
No, if you start out with 12 volts and set it to 3 volts, and then you drop that input down to a 9-volt battery, your output's going to drop. Okay, you'll have to go back in. You have to go back in and readjust it.
Okay.
Okay. But that's all you need to do is just go in and turn that screw a little bit until it comes back up to 3 volts.
Yeah, I've always set my LEDs up for 12 volts, just anticipating, that it would be on the layout pulling 12 volts.
Correct. Yeah, I work with 12 volts as a standard too.
But then when I want to take it somewhere, I have to have a 9-volt battery to be able to power it.
Yeah, yeah, but it doesn't take but a minute. Slap that 9-volt in there, turn that screw until it reads what you want, or you
Just
can ignore. You can ignore that meter and just eyeball it. Just turn that screw until you get the brightness that you want.
Mm-hmm.
Okay. Somebody else had a question, I think.
Yeah, just a comment. I guess going back to the Arduino, I guess there's no reason why you can't use the digital outputs to control a 5-volt relay to switch 12 volts onto LEDs.
That's correct. You can use that. They make a lot of attachments and accessory boards to go with these Arduinos. That's
I already have strips of LEDs with a built-in resistors that operate on 12 volts.
Yeah.
And have these little electronic relays. I think they operate on 5 volts. That you can switch whatever you want to.
That's absolutely true. The thing that you have to watch though is that if you start pulling current off of an Arduino, they're only rated for 400 milliamps maximum.
Well, and that's the reason why I was thinking that might be a better use of them, because you know, a momentary relay contact closure is not going to cause, like in a random program like what you had going.
Yes.
Drawing
Okay, I
much
see.
current.
You're talking about using a latching relay. Okay.
Well, actually, it's electronic relay, but once it closes, it doesn't pull any more current, I don't believe.
Okay, that would be yeah, that's an electronic version of a latching relay. I understand
Right.
what you're saying. Yeah.
Exactly.
Mhm.
Yeah.
Okay, yeah, there's a lot of accessories that are cheap and easy to get to go with these Arduinos. There's a lot of already pre-written code, even for model trains. They're doing, Arduinos are being used as DCC drivers for trains. You hook them up to a booster, of course, to get the right power, but they talk DCC if you want them to. So you can make your own controller if you want. Okay, they're that useful. Okay, there's a lot out there that you can do with them.
For those of you that can see, I'm showing an electronic relay board here on my screen.
Have you dropped down and done a screen share?
No, it's just on my camera view.
There it is.
You can see let's see, these are, it looks like 8 channels, 8 different relays that can control the output.
Yeah.
And these are cheap. I got this on eBay for $4 or $5.
I've actually built I/O cards with the Arduino in them so that I control transistors and outputs. I've got some that talk the IC squared, so I can control servo motors. I designed my own cards, and I have them for sale, $20 each. I'll put that up later.
Oh, so this is one big advertisement, huh?
Yeah. I had fun building them. If you want them, they come with me. I'll come over and help you hook them all up. Do all
Oh, we
that
get
stuff.
customer service too, huh?
Yeah. Okay. I enjoy the wiring and the challenge. That's my cup of tea.
That's cool.
Any more questions?
Jim, I had a question. This was from Chuck Wind. He's dropped off, but he had some 2-color LEDs, the red and the green.
Yes.
He was not happy with the brightness between the two was not uniform.
Right.
Is there a way around that, or a different LED, or he's decided?
Yes. What you do there, you can either do it externally with a variable resistor, or you can do it to an Arduino. If you're doing it to an Arduino, you hook the one lead of the LED to one output, and you hook the other lead of the LED to a second output on a pulse width modulator pin. And then you control the frequencies going out to the red and the green. And you change the number in the computer until you get the right balance, so it looks yellow to your eye. If you do it externally, the red is always brighter than the green. It takes less power. So when you put the power out, you put a variable resistor on the red lead, and then you tweak the brightness of the red until the red and the green mix to make your yellow. That make sense?
Yes, yes.
Okay.
One other comment that I might make is you might go ahead and put on the Division 8 website links to those 3 different products. And that way it would be easier for us to find them and get the right item.
I can do that. I can do that. Yeah, I'll put the links in my write-up. That's a good idea. Any more questions? Again, if you want more depth on this code, I can do a Zoom one-on-one with you, and we can walk through the lines of the code one by one until you understand what's going on. I love to teach. Okay, guys?
Jim, just one question. Are those programs that you've created, are those available as electronic files?
I'll put them on my Google Drive in a link where I'll share them. Okay.
Okay,
And then I'll give you the link to the Google Drive, and you can download the files directly.
that'd be great.
Okay.
Fantastic, thanks.
Any more
Thanks for
questions?
this- Thanks for this presentation, Jim.
Okay.
I know I came in late. I had some other stuff to do. But good job.
Johnny, you're looking good. I'm glad to see you home.
Glad to be home.
I bet you are. I bet you are. Take care of yourself, okay?
Oh, yeah.
I miss running trains with you.
Well, we'll get back to it.
Okay. Yeah, as soon as this virus lets us.
Yeah.
All right, guys. If there's no more questions or anything, I'm going to let it go. I'm recording this. I'll post it and give you a link. That way you can stop and replay it. I'm sorry I had some difficulties along the way, but this is the kind of stuff that really should be done in the classroom with you watching. It's hard to do over video. But I think we had fun with it.
Great.
Thank you.
All right.
Thank you, Jim.
All right. Bye-bye.
Okay.
Thank you.
Thank you.
Thanks a lot, Jim.
Six, 2, and even, over and out.
Okay.
Bye-bye.
Bye, Scott.